Okay, go ahead.
Okay, hello everyone. Today we are going to talk about adjoints. We're going to discuss some properties of adjoints and hopefully, well no, definitely, we are going to prove the spectral theorem, or, a version of it anyway. But before we do that, for the definition of the adjoint to even make sense, we need to go back a couple lessons to, this result, which we didn't name it, but we've basically proven it, the Reese representation theorem. So if V is a finite dimensional inner product space, then for every functional phi on V, there is a unique V in the vector space such that that functional is basically like taking the inner product with that V for all U in the vector space.
And in this case, you really want to, for our convention, you want to swap U and V in.
Yes, I suppose
yes.
we do. But you can also just consider like the conjugate.
Yeah, sure.
Yeah, it doesn't. I'm using Axler's conventions.
So okay, sure. Use whichever convention makes most sense.
For now, let's just consider the linear map, and it's going to be a linear map that takes any vector v in the vector space to sort of this function where you take, like, let's say you put in some vector u from the vector space and you get the inner product of v and u, and this is obviously like a function from v to r, or from v to the field, and you can sort of convince yourself that it is actually a linear map because this the inner product is linear in the first entry, right? Now, when we have a linear map, well, we have basically what is a linear map between the actual vector space, and this is a linear functional then, and they're both, we have that they're both of equal dimension. And so for this theorem to be true, we just need to make sure that this linear map is a bijection. And what we know is that if you're working with vector spaces of equal dimension, that you only need to prove like one of either injectivity or surjectivity to get a bijection. Injectivity is easier in this case because, well, here's the argument. You just plug in V, and then the properties of the inner product tell you that if the resulting linear functional is equal to 0, then you plug in V to get that the linear product of V with itself is 0, or the inner product, is equal to 0, and then the properties of the inner product tell you that V is equal to 0 then, because the norm is 0. And so we have injectivity, yay! And that's enough to get a bijection.
So actually,
yes.
I now understand what you were saying earlier about R. You're kind of right, actually, because look, if I want to prove the result above where I have U comma V, then I really want to be sending V to, the first slot is empty and V in the second slot.
Yes.
Okay? But then that's not a linear map, that's
a skew,
skew linear map. And then I think all the properties for skew linear maps it's still going to be all the same, right? As far as it will still have rank nullity in the same way.
Okay.
But then you're right that is some additional comments need to be made there to show that it works.
See, because like
and I didn't realize this like a few minutes ago.
Because I thought like the proof in Axler actually does surjectivity and injectivity like separately.
Yeah.
And I think he wouldn't do that if he could just like get away with.
Yeah, exactly.
So let's just say this works for R.
Yeah.
For C, there's some like additional work that needs to be done. We're not going to worry
Yes.
about it. Whatever.
That's true.
It still works. Is what the important part is. It doesn't even matter that. It doesn't really even matter that much that it's a linear map, or it's not a linear map. It just matters that it's a bijection.
So did you get what the result of the Reese representation theorem was? What was the statement? Okay.
Okay.
There's a linear functional on V, right?
Yes, there's,
And then-
like, take any linear functional
Yeah.
on V, right? From V to F.
Yes.
Yes. What can we say about it? What, the Reese representation theorem says that for any functional, there's something we can say about it.
The inner products are like.
I can write phi as an inner product.
Yeah, there's such that phi is equal to this.
Yes. So, applying phi to any vector is the same as just taking the inner product of some vector with V.
Okay.
So like.
It's an
yeah.
identification of
Yeah.
sorts. Yeah.
And remember, I don't think you were here, maybe you were.
Yeah, I was.
We had some, I mean, you probably did this in 247. You know, if you had your vector space and your dual space.
Yeah.
If you choose a basis for the vector space, then that automatically gives you a basis for the dual space.
Yeah.
Do you agree? But that map depended on the choice of basis. I choose a different basis, the map is completely different.
Doesn't work.
Okay.
Okay.
Well, it works, but it's just a completely
Yeah,
different
yeah,
map.
yes.
Right? The isomorphism is basis dependent. Here, we see that if I have an inner product space, so I have an inner product defined already, then that uniquely determines this isomorphism between V and V dual. Right? Given an inner product, there's like a natural isomorphism between V and V dual.
Yeah. Exactly.
Do you see this?
This is
Right, because what this is really just an isomorphism, saying that if I have V, then I have a linear functional like that. And I mean, I guess it's not quite a linear isomorphism, it's a skew linear isomorphism, but the same idea. Right, so kind of this additional structure fixes how I can relate V to the dual space. Important part is this Reese representation theorem is only true in finite dimensional
Yes,
vectors.
it is.
Yes.
Yeah.
Because in the proof that we just kind of sketched out, we used rank nullity.
Yeah.
And rank nullity does
Yeah,
not work
yeah,
for
yeah.
infinite dimensions.
Yeah. And you know, the proof for the complex version, it uses like a orthonormal basis, which also.
Yes.
Yeah. So now we're going to make use of this wonderful fact to define a very special kind of function. It's called the adjoint. Now, the adjoint, denoted T star, is a function, not necessarily a linear map
So,
yet.
small comment. Before, we were using star to mean the dual map.
I know.
So, and because Axler uses dash for the dual map and star for the adjoint. So maybe, okay, you
I
can
could
keep
do
with
like
star
that.
if you want,
Okay.
but we can also use dagger.
Okay, sure. Let's use
So
the
stick
dagger.
with physics notation because physicists will eventually you'll use dagger. Yes.
The dagger.
Yeah.
But Axler uses it for the pseudo
Is it a
inverse,
relation?
He
which
uses it for what?
the pseudo inverse.
Okay.
But
I see.
whatever.
But this is more standard in physics.
Okay, this
and
is
you'll-
more standard.
You'll do this for now.
So yeah, so the adjoint is a function from. Okay, hold on.
Let's first say what
yeah.
T is.
Let's first say what T is. Let T be a linear map from V to W.
Where V and W are what?
Where are V and W? V, W, or I suppose. Well, they don't have to be finite dimensional, but they have to be inner product spaces.
Yes. Yeah.
Yeah. So the adjoint is a function from W to V, such that the inner product of T V with W is equal to the inner product of V with T dagger W for all V in V and W in W.
Okay. So small small comment?
Yes.
Use, I don't know, maybe a different color chalk, and put subscripts on the inner products to point out that one of them is in V and the other one is in W.
Okay.
This one is in no.
No.
It's
Uh,
TV,
yeah,
right?
Yeah,
So it's
no,
in
that's
W.
right. That's right. That's right. This one's in W, and this one's in. Yeah, that's correct.
Cool.
Sorry.
Okay. So yeah. Great. So the adjoint. Why does this definition make sense? It is because of the theorem that we just proved. Because, well, you see, for this to be true, you know, you see this function here, right? If we think of t of something with w, this is a linear functional, right? It takes a vector in V and gives you like a number in a field. And then by the Reese representation theorem, which unfortunately you were not here to see, but there exists a unique, some kind of unique vector, and that exact vector is t dagger w, right? Such that this linear functional for this product equivalently is equal to this product for all v. And so this works for each w, and so we have a function. Right. Does that make sense? Yes? No?
I think you should stop. You should
Okay.
wait, take a sip, and then say some more sentences about it.
So, I suppose, should we do an example maybe? Would that be
Okay.
helpful?
I think that could be helpful.
Okay.
I think, sorry, I'll just kind of
Yeah.
skip ahead to the end. The comment that I would give you at this moment about presenting is you said a lot of things, but you wrote down very little, right? So in terms of me looking at the board right now, doesn't help me remember the things that you said in the last 2 minutes, because you've been mostly saying and not writing anything down. So I think if you had as far as how the proof went,
Okay.
right? So it's writing a little bit more would be helpful.
Okay.
Because just people miss a phrase, and then they missed it, and there's no way for them to rehear it back or remember what was said unless something was written down.
That's fair.
Yes.
Yeah.
But that's okay. No worries.
Okay.
Alternatively, you could ask a question.
Okay. Why does this work? Is this something I just
So
explained?
I guess okay. Let's ask a different question.
Let's ask. Okay.
So, here we had what? We showed that, so I want to say, I have this map T from V to W, okay? And I am saying, suppose I had this map T dagger that had this property, that T of V inner product W was V inner product T star T dagger W. Okay? And so the point is, I want to show that this map exists. Because, okay, I'm saying I would call it, if there was a map with this property, I'd call it this, but let's show that it exists indeed, okay? And so then the argument was what? We said, oh, well, I have Reese representation theorem, do you agree? And Reese representation theorem went like what? It went that, okay, if I have a linear functional, right, then there exists a vector that I can write this linear functional as inner producting with some particular vector. Do you agree? And so now I say, okay, well, I have a linear. If I so write down the linear functional again for this case.
Okay. So
it's
for this case,
right. The linear functional is
Linear functional. is
write the linear functional as phi of v, so that there's a clear what the input
phi
is.
of- yes.
Yeah,
Yeah.
that's good.
Phi
Phi of v
is equal to this
CV
our
inner
inner
product.
product.
Okay. This is a linear functional on what space?
This is a linear function.
No, it's not a
On
question
W-
for you.
W?
Okay.
No, where does it take input?
Oh, from V
From v. So this is a linear functional on v.
to W.
That inner product is in what?
W.
In W, okay? But Reese representation, this is a linear
Yeah.
functional on v. So Reese representation theorem I have on
V as well.
v. So this means there has to exist,
Some.
so do v inner product some like u or something.
Okay. Let's do. Yeah. Sure.
There exists a u, just so that we're
And
literally following the theorem. Yeah.
such that I e is equal to
Yeah. Okay, good. So this is, we fixed v, and we said that for a given v, I can find this u. Okay? But now, what I can do is I can just define a map using this, and I define it in what way? I define it as t dagger of w is defined as
this.
this. Okay? So this was, sorry, this is we fixed w, and for a given w, we told you how to map this w. Okay? Using the Reese representation theorem.
I don't know. Wait. So wait, how'd you define it like this?
Which.
So I said, let's see.
The last step right there.
The last step.
Yeah.
So, okay, I said, I have this,
Yeah.
right? And I can think of this as a linear functional.
Mhm.
Then by Reese representation theorem, there exists a vector u such that this inner product, so for a fixed w,
Yeah, yeah.
this inner product is equal to this inner product.
Mhm.
Do you agree?
Yeah.
And now I can say, aha, I want, okay, so this is equal to this. Do you agree? So now I just say, okay, let me define some linear operator, and I can just tell you how that, not even some linear operator, some function. I define you some function. So to define some function, I need to tell you how does this function act on the vectors. So I tell you, let's
Oh.
define something that, given w, it finds the associated u and sends it to the associated u. Okay?
Now I'm saying.
There we
Yeah.
go.
Okay. Makes sense.
Yes. So now the question, because I still haven't asked my question. Now the question. Okay. So, can we, just from this, try and kind of guess what the matrix of T star is going to be?
It's transpose.
Okay, you're right. But remember how that's half the answer. Well, that's like 3/4 of the way there.
Okay. Okay.
It's the transpose, but with what else? Because remember, I said something about like, oh, the map is not linear, it's skew linear, so there's some complex conjugate involved, so what should I do?
It's just the conjugate transpose.
Exactly.
I see.
Why is this the case? Because, I'm taking W and sending it to some vector that's associated with the right kind of linear. Actually, sorry. This is what I'm saying is not entirely correct because the matrix is the conjugate transpose only for a special kind of basis.
Yes.
But this is kind of intuition for why roughly that will be a sensible result to get.
Yeah.
Is it matrix?
Hmm? T is a linear map, and
Yes,
then you can write
we're
down.
going
Oh well,
to.
sorry, I'm spoiling.
No, that's fine. I mean, we're literally about to
Yes.
close. This is the next result. Okay.
It will be a linear map. So
it
we
will be.
have some basis.
It will be a linear
well.
map in about 5 minutes.
Yes.
So, we're doing linear algebra. We like the linear maps. We like T dagger to be a linear map, if possible. Well, turns out it is. Let's prove it. It is. Okay. So, we need to prove two things, right? Additivity and homogeneity. It's called additivity. So let's say we have let's see, goes right right V
Yes.
and
That's me.
W1, W2, in W, we have TV, W1 plus W2 is equal to, on the one hand, the T adjoint T dagger W1 plus W2. And on the other hand, it is also equal to, we can split it, right?
Oh.
To the inner product of TV with W1 and W2 separately, and we get, and now we apply sort of the adjoint to get T dagger W1 here, and T dagger W2 here, and then once again we use sort of the properties of the inner product to get this. And so you see, here we have that this inner product is equal to this inner product for all V and V. And so we can consider like basically this linear functional, you know, just taking like any V and then assigning it to this function, or well to this, I guess, number it would be. And then we can consider this linear functional. And we know that they're the same because they're equal for every V and V. Does that make sense? And so by the Riesz representation theorem, we can say that these two sort of terms are equal. Because, well, yeah, it's the Riesz representation.
Sorry, so
Yes.
this being non-zero for sorry.
Yes.
Why does it follow that because this is true for every V that those two things are equal?
So we have, okay. So
Hold on, do you understand what I'm asking?
Maybe you need to show that the kernel is 0.
Of what?
The
We are trying to show that it's a linear map. We can't even say that it has a like kernel in a usual sense.
Okay.
So sorry, the point I'm trying to make is he showed that okay, V inner product T star of something is equal to V inner product T star plus T star. Right? That's what he showed. But how does this why does this necessarily imply that T star T star of W1 plus W2 is indeed equal to T star T dagger W1 plus T dagger W2, right? Like, do you see how saying that is equal to that, and saying that implies that TW1 of W2 is equal to T star W1 plus T star W2? There's like, it's a non-trivial step. Like, there's something else that may be involved.
Invariant? Maybe?
Sorry, do you see what do you understand what the question is at least?
Yeah.
Yeah, okay, good.
It's not like as trivial as a lot.
Yes.
Yeah.
So the question is, we once again use the result from the beginning, which was Riesz representation theorem, right? So now what we say is like, okay, suppose we have that is equal. Okay, you say it. Sorry.
Yeah. Okay. So like we consider these two as sort of linear functionals, right? So you know I have these written out. So like we have the first linear functional,
Just like last
which
time.
is yes, just like last time. That takes V and takes the inner product of it with this thing, and then you have the second inner product, or the second linear functional that takes V and gives you the inner product with this other vector. And we have, we just showed that these two linear functionals are the same. By the Riesz representation theorem, there is only one vector for each linear functional, such that they're equal to some
Yes.
I see.
some other product. Yeah. So this is equal to u, and this is also
Yes.
equal to
Yes.
u.
So
Okay.
there's like a small non-trivial step, and that step is once
Yes.
again the Riesz representation.
Yes.
In the third edition of Axler, I don't think, or at least maybe that was in the third edition of Axler, but when I took 247, this was explained in a much more confusing way, where we kind of picked an orthonormal basis and then computed it, or something like this. And I remember that when we were defining T star, we did not mention the Riesz representation theorem whatsoever. We just said that, okay, I want something with those properties, and essentially figured out what its matrix elements have to be in some orthonormal basis. And that was just confusing.
Axler keeps winning.
Yeah, exactly. Axler keeps winning just by having better and better additions.
Yes. Okay. Can I erase this? Is that, yeah?
Yeah.
Okay. So that's additivity. And, like homogeneity, which is like scalar multiplication, it goes fairly similarly.
I mean, it goes not fairly similar, just identical.
Pretty much. So yeah, we have let V being V, W being W, and then lambda being F, right? And then we're looking at T of V with lambda W is on the one hand equal to V and T dagger of lambda W. On the other hand, it is also equal to this of T V W, and this might be a little scary. You get a conjugate, but it works out. So just keep doing this, and then you take it back in. Bam. And so these two are equal. And so, by the same logic as last time, this is equal to this.
What was that first step?
It was, which one? This one?
Yep.
Okay, so we have this, and then we apply the definition
No,
of the
the-
adjoint directly.
Yeah.
Okay, so, yeah, so.
That's by the
recall-
definition of the inner product.
Yeah, recall that the inner product is skew symmetric, skew linear, whatever it's called. And so, like, when you have a scalar in the second entry, then when you take it out, you get the conjugate of that scalar. Because it's like, here, you have u lambda v, this is equal, by the definition, to this is v, no, this is v, this is u, which is equal to, you take it out, because it's linear in the first entry.
Oh, and then you flip it back.
Yeah.
And then,
Okay.
yeah.
And so remember, the skew symmetry, we needed that to make sure that V inner product V is always a real number.
Yeah.
So that we can have a sense of the length of a vector. Right, because if I had V inner product V, and then I had linearity in both entries, then if I multiplied by complex lambda, I'd get complex number times V, and so it might be non-negative. But if I factor out a lambda from the first entry and the lambda bar from the second entry, then I get lambda squared, like the norm absolute value. And so I guarantee that I always have that V inner product V is greater than 0, and a real number. Yeah.
Okay. Great. So yeah, that concludes the proof. And now we know that T dagger is in fact a linear map, Now, the next step is to prove some basic properties of this adjoint. Okay. So here's sort of the second, I guess, theorem, whatever, properties. For T over the following properties. Hold. Okay. So I suppose yeah. Yeah, let's see. T and S from B to W. Let's put it this way. So yeah, because we're going to need multiple linear maps for some of these. So the first one is that the adjoint T and S is equal to the adjoint of T plus the adjoint of S. The second one is that the adjoint of T and S multiplied, or I suppose, hold on. TNS. You can infer from the context what the the domains and the codomains of TNS are. We're just gonna assume that it makes sense. So the adjoint of T times S, or T of S, is S adjoint, T adjoint. So you flip the positions here. The third, what's the third one? Well, let's go with this one. The third is that the adjoint of the identity is the identity. The fourth is that the adjoint, well, if T is invertible, then T inverse adjoint is equal to T adjoint, T adjoint inverse. And there's one that I'm forgetting, which I'm going to look up right now. Let's see.
What's the third one?
The third one is that the adjoint of the identity is the identity.
Oh, okay.
This is not.
So I guess in this case, before we're saying from V to T is from V to W, but okay, W could be just V and it could be a linear operator, right? So.
Yeah. And then the fifth property is that if you multiply it by a scalar, then you get, you take it out and you have to take the conjugate, and then you get this. Okay. So I'm going to move over to that board now. I'm going to erase all of this. So yeah, I mean, these proofs fairly easy for routine, kind of following what is basically like the same format we've been doing this entire time. So yeah, so let's do the first one. We take T plus S of V again, A and W, like, just like any two vectors. And then we have, on the one hand, again, V T plus S dagger W. On the other hand, we have TV plus SV W, and we split it, TV with W plus SV with W, and then we take the adjoint of each one, or apply the adjoint to each one. So we end up with this. And then, you know, you just take them and again add them together.
One of them supposed to be an
sorry.
S.
Yeah,
right?
that's yeah. And so yeah, and so this is equal to this. Yay. Second property. Yeah. So we have T of S. I'll stop writing this part out because just to save time, space is
You
equal
can write it at the end.
to let's see. Well, no, hold on. There. Then we can take. Let's get rid of these. So we can take T over to the other side right now to get S of V and then T dagger of W. And then we can do it once again with S now. And then we get V, S dagger, T dagger, W. And this is equal to T's dagger, W. These are equal. Cool. That's the second property done. It's not too big. Yeah. The third one, so you know, I of V with U is equal to.
I mean, you don't have to prove the third one. The third one, I believe. Yes.
Yeah. Alright. It's easy enough, sort of. So the fourth one, yeah, okay. So we have, you know, that T minus 1 times taking T is equal to I, right? Now we use the second and third properties to get that, you know, I dagger, which is equal to I, is equal to, then we take T dagger, yes, and T adjoint dagger, or sorry, T inverse dagger. Yeah. On the one hand. Then we also have that T and T negative, or sorry, T inverse is also equal to I. You know, we switch the positions. And then same thing. We take the adjoint, I, and we get T adjoint, T adjoint. So we have that, you know, we have T adjoint here and T adjoint here, right? And then we have the adjoint of T inverse here and also here. And so like we have the adjoint of T inverse is the left and right inverse of T adjoint. Then, sorry. Then it is just the inverse. Great. And then finally the fifth property, also fairly simple. We take T of V with W is equal we can take out lambda. We can also apply the adjoint to get this, and then we take it back, and we get the lambda. Yeah, we take the conjugate t dagger w, and this is equal, to so these two are equal. There we go. Does that last one make sense?
Think so. Yeah.
Yeah. Okay. Questions? No. So those are the basic properties. And now that we have some of those, we're ready. I suppose I don't think we even use any of the basic properties, but whatever.
I think we use the scalar lambda one. It's kind of useful, I think.
Do we? Maybe. I don't know. We might use them. But okay, I'll get rid of this for now. So now we turn our attention to the matrix of Ti joint. Ooh, and you've already sort of guessed that it would be the conjugate transpose.
But remember,
yes.
it's important. Whenever I say matrix, you always have to ask in what basis.
In what basis? Yes. And in this case, the choice of basis is fairly. It's important. Theorem. Let V W be finite. Right? Yes.
Yeah. Just write FDM or something, or no, FDV. Finite dimensional vector spaces. Write whatever. It doesn't matter.
Inner product space, actually.
Yeah.
Inner product space. Yeah. Finite dimensional inner product space. Let E1 through En be a basis of the an orthonormal basis. That's the important part. Let F1 through Fm be an orthonormal basis of W. Then I suppose let's call these beta 1. And then beta 2. Then
the better notation for that is just E without subscript and B and F without subscript.
I suppose, yeah.
I think that'd be a little less confusing. Or maybe more, I don't know.
It's fine. Then, yeah. Well, T is a linear map from V to W, I forgot to say. But then, the matrix state, the matrix of T, with respect to these two bases, is going to be equal to the, or I suppose we haven't defined the notation for a conjugate transpose, so I'll just do this. Let's write it like this. The, yeah. So we take, this is the matrix of T dagger, right, with respect to these two bases. And the adjoint element of this matrix is going to be equal to the transpose of the ji entry of
this is where you once again pause and take a sip.
Okay.
This has a bit.
Oh, you said transpose, but then you did conjugate?
It's the conjugate transpose, yeah. So you take the transpose and then you take like the conjugate of each entry.
Yeah. You flip and put a bar over everything.
Yeah. Okay. Questions?
And so it's important that this is true in an orthonormal basis only.
Yes.
The other thing is, the fact that it has to be a transpose was also kind of clear from dimension degree. T goes from V to W, so the input is V, the output is W. Okay, but then T dagger goes from W to V. So input and thing have to be flipped. So it being a transpose also makes sense in that.
Yeah.
sense.
So yeah. So let's prove it. The proof is fairly simple. So the first thing that you sort of have to notice is that if I take
Well, hold on.
yeah.
How do we prove a thing like this?
Using the properties?
Sure. What's the approach?
We have
So the question is, what is a matrix?
Yeah. Like the linear.
What is a matrix? What is a matrix?
what does a matrix?
That's the
what
new
does a
question.
what's the definition? Yeah.
Yes. What is a matrix?
Like if when we take like T with respect to B, you know,
And
what does
the
that
ijth
mean?
component, what does it mean?
What
What is
does-
the ijth component?
Just the index?
Okay,
No,
let's
look. No,
here.
stop.
Uh,
Give him some time. Don't tell him the answer. So look, I write
Like the change
matrix
of
of T dagger from F to E,
Yeah.
and then I write ij.
Is it the change of
What is
base?
that number? Where does this number come from?
The what number?
Oh, okay. This degree over here, this is a number.
Yeah, yeah.
What is that number? Where does it come from?
The first.
Hmm? The what?
The first index? Like wait.
Of what?
Of the change of basis from. F to
No, it's too hard. We change of basis. I don't know these
Okay,
words.
Okay.
I want you to give me an answer in terms of T star F E I J. Give me an answer in terms of the things written on this board.
maybe it would maybe like let's first think of the columns. Well, we can think of
just
the
give him just don't give him any hints.
Okay.
Just have him think. He should know this. This is I've said this in office hours so many times.
I've
You
never
can't-
come
you
to your
can't-
office hours.
Well, skill issue. You've come to tutorial, right? I've said this in tutorial almost as many times as in office hours. What is a matrix? What are the entries of a matrix? What are they? No. The entries of a matrix are numbers. But how do I get those numbers?
What do those numbers represent?
Yes. What do they mean? Where do I get them? Right? So I give you T, I give you input basis, I give you output basis.
Yeah.
How do you come up with a matrix now? From that. Okay, let's think about this. So if I have T, right?
Yeah.
What does T do? Or T star or whatever, T dagger, what does it do?
It goes from like B to the.
No, what does it do?
Takes a vector.
Takes a vector.
Yeah.
So we should apply some vector. Okay. If it's T star, which vector does it make most sense to apply it to? T dagger.
Yeah.
Which vector does it make most sense to apply it to?
F something.
Yes. So let's try and do F sub j to it. Okay. Good. So this is going to be equal something in terms of that I can write in terms of what?
E.
E. Good.
Yes.
So I have right linear so right sum.
So for now at least, I guess I'll.
Yeah. Just
Yeah.
do this.
We have n. So yeah, this is just a vector.
Yes. But now, okay, remember, the coefficients in the matrix were what? They are numbers. Can you find some numbers in this situation?
Like from A1 to
Yes, A1, A, okay, those are numbers.
Yeah.
Beautiful. So now we define the matrix coefficients to be
those numbers.
those numbers,
Yeah.
precisely, where I index instead of A1. So A1 is going to be T1J,
Yeah, yeah.
T dagger 1J, okay, so on and so forth. Good. So now that we figured out what a matrix is, if this is what a matrix is, how do I compute, I gave it away. How do I figure out what T dagger FEIJ is? What do I do?
Input the basis.
Yeah,
Okay.
that's it. I just
Yeah.
apply T dagger to the basis, and then read off the matrix of entries.
Okay.
Okay, that's it. That's all there is to it.
Okay. Yes, I'll go ahead with the formal proof.
Sorry, yeah, go ahead. Sorry, I'm wasting time. I'm wasting time, but this is
Thank
like.
you, thank you.
This is important.
I feel, yeah, knowing
This
what a
is important,
matrix
this
is
basic.
relevant
Yeah.
to the course, to everything. Yeah.
So yeah, so like, you know, as we said, for each fj, you know, the matrix would look something like what we're getting here are sort of the numbers for the jth column, right, of the matrix. So we have that this corresponds to like A1J, so on and so forth, to A and A and J, right? Now, here's an important part. This is an orthonormal basis, and one of the properties of an orthonormal basis that we proved is that these guys, for any vector, right? For any v, if you have like this, then you can write it. Then each of these coefficients is equal to the inner product of v with that
EI.
that component vector. Yeah.
Yeah.
And so on. So that's just like a property of orthonormal bases. And so here, you know, we apply it to our case here with T dagger of fj, and we get that each
AI,
of
you did
these,
write AIJ?
yeah. Let's just do a sum. It's going to be equal to the sum of T dagger fj and EI. Multiply that by EI. I is 1, 2, and right. Now, the ijth entry of this is going to be, well, you index the ith sort of the ith component vector, and you get that T dagger of what we're trying to find, ij, is equal to T dagger of fj ei. Great. Now we have it in the form of an inner product.
But what did we want? We wanted to figure out what that matrix element is in terms of matrix elements of T. So we want to rewrite this instead of an expression in T dagger to an expression in terms of T.
Just use.
Crap.
We use what?
I forgot an important property.
Yes.
We're going back to this. Okay, this is.
I don't think it's.
Well, I
If the
suppose
T is
you,
going to
you
T
don't
dagger.
have to, but it's like a very
Okay.
T dagger.
Okay.
T dagger is what? Just
T. Yeah.
That's what you want. Yeah. Okay,
Yeah.
Okay. Okay.
Yeah. I see.
Yeah.
Yeah.
Okay.
And
Yeah, yeah.
I mean, this is easy to prove. Yeah. Does everybody see why this is the case?
I mean, I assume that was the case, but what would the proof be?
Okay. So T dagger of V with W
Yeah, yeah. And then you find
is equal to, yeah, you basically what you do is
Yeah. You know that to like
You take
you yeah.
Conjugate.
Well, you
You swap. You
You
take the
swap-
conjugate to swap the order.
swap the order.
Oh,
Yeah,
right, right,
but
right.
then you know that T of W, that
And then you like
that this, and then you swap it back.
swap it again.
I see. And so then you know that the adjoint of T dagger is just T.
Oh, okay. Okay.
It's very straightforward.
Yeah. It's yeah. So yeah, going back to this, we take, you know, the adjoint, the double adjoint, which is just the original method. So this is equal to this, right? And from here, it is simple enough. We just need to do this. And we're done. Why are we done?
Because that's basically that.
Yes. Yeah. Because this is the sort of ith
In-
column,
Yeah.
Yeah.
and this is the
Yeah.
jth row. So yeah. Great. So we have this nice result about the matrices, the matrix of the adjoint. So yeah, I mean we can just kind of move on, I guess.
Yeah.
Yeah.
Now we're in position to just prove the spectral field.
Now we're
which is the
in
important
position.
thing.
Yeah. We're in position to define the self-adjoint
Are we gonna find
and then
ghosts?
yes. Wait.
Hmm?
He said yes. We're gonna find ghosts.
We can find
Ghosts?
ghosts. We can find ghosts. Yes. Sure.
There are ghosts, but the ghosts that I know about are somewhere else. Did I ever tell you guys about the Holy Ghost? Well, it's not the Holy Ghost; it's the Holy Hammer that acts upon the graveyard of that is your vector space. I never told you about that. Okay.
No.
I'll maybe one day.
Okay.
It's an amazing analogy for generalized eigenspaces that was shown to us in Math 240. In
Holy
fact,
hammer?
if you go to PhysU and look at the tile on the ceiling
Is there a holy
for
hammer?
2020, for last year, for 2025, you can find a reference to that analogy in that tile.
I looked at all of the tiles.
It's
Why do
not
I
it's
do I
not
not
very
remember
big.
it?
I mean, it's a very particular thing.
Oh, is
You-
it's like small?
it's fairly small.
Oh, okay, okay. I was just sitting there once and so I looked
Yeah.
at all the tiles. And
Yeah.
yeah.
Yes.
Okay. So, now we come to a very important definition, I suppose. This is a specific type of operator, a specific type of linear transformation. T, as a linear map from V to V, is self-adjoint if T is equal to its adjoint. Makes sense, right? And so, you know, in terms of matrices, what that means is, well, you know, we have the matrix of T dagger is its conjugate transpose. So, you know, the matrix of T is equal to its conjugate transpose with respect to orthonormal bases.
Yes.
Yeah. And, you know, since we're working in V, we can take, like, these F's and these E's to be, like, the same basis, because it's an operator, right? And so, like, the matrices, these kinds of matrices are called Hermitian matrices. We'll talk about them in 247, and, you know. And I suppose now would be a good time to mention that there's kind of an analogy between the adjoint and sort of like the conjugate of the complex number, I was told. So like, for example, take any t. If you take, consider the linear map t dagger t. What happens if we take the adjoint of this?
Is T adjoint? T's
remember,
T.
You have to
the order is
swap.
swapped.
Yeah,
Yeah,
you
yeah.
have to swap the places.
You have to swap the order.
Yeah,
So you
T
take the,
adjoint.
so you have T dagger T.
Oh, sorry, yeah, T dagger
T.
Yeah.
It's still T dagger T. Because you
right.
swap the T, you swap their order and then take daggers of both.
Okay. Sorry. And that's just T.
Yeah.
Okay, sorry.
So it's kind of like, it's, you know, so like, you know,
Right,
the,
sorry,
the
there was two
adjoint is
sides.
the
Yeah,
conjugate.
yeah.
So if you take, and self-adjoint
Mhm.
matrices are kind of like, if a complex number is equal to its conjugate, then what kind of number is it?
Real?
Yes.
Yes.
So self-adjoint operators are kind of like real numbers in a
Mm.
sense. So, and you can see, like, if you take any operator and take it, or any, I guess, linear map, and take it with its conjugate, or its adjoint, then you get a self-adjoint operator. Just like if you take, like, Z conjugate, this is going to be a
You know what? This is great inspiration for you to prove a theorem on the spot.
yes.
The theorem is going to be what? Let T be self-adjoint. It's a very easy theorem. Let T be self-adjoint.
Yep.
And V an eigenvector of T. And V, don't write eigenvector, and V such that TV equals lambda V, just write that. Equals lambda. Question for everyone. What kind of number will lambda
Real.
be?
Real.
Yes.
So yes, so the statement is then lambda is real. And then we prove this.
So I'll just go ahead with the proof. I
Yeah.
suppose. Right? So we have, consider this inner product.
Yeah.
We have that this, you know, is equal to lambda v, which is equal to, you know, on the one.
Yes.
Lambda v times, but yeah, the inner product of v would be. On the other hand, if we apply the adjoint first, give me a second.
Wait,
Hold on.
do we have the next step?
Yeah.
No, I think that's fine.
Yeah. No, that's correct. Because this is, the adjoint is just like itself,
Yeah.
right?
Because T is self-adjoint.
And then we get,
Right.
we get this,
Uh-huh.
and then we take it out and we get the conjugate here.
Yes.
And we know that V
Yeah.
is an eigenvector, so it's not equal to 0, right? And what we know about inner products is if you don't have, if V is non-zero, then its norm, or
Mhm.
the square of its norm is not equal to 0 either. So we can like cancel these out, and we get that lambda is equal to lambda conjugate. It's real.
Yeah.
Yeah.
That's right.
Wonderful. So yeah, that's really.
So, yeah, okay. Let's make a further comment. So we see that the eigenvalues are real. And then above we said something like, oh, the self-adjoint operator is almost like a real number. Do you agree?
Almost like real number.
Yeah, like
Okay.
right. So, like in some loose sense, whatever that means. Okay. So then, you know, and the eigenvalues are real. And you know, what's the closest I can get it to be a real number? Like, what might happen? Like, think of its matrix. What would be really nice if the matrix was this thing? The identity close,
Sorry.
but maybe, I mean, good guess. That's a good guess. The identity, but that's too much.
Okay.
Maybe I want not the identity, but at least diagonal.
Okay.
Do you agree?
Yeah.
maybe different entries. But then those entries I know will have to be
Eigenvalue.
real.
Oh, real.
Right, and the eigenvalues.
Yeah, yeah.
That's right. So in other words, a reasonable thing to try and think about is to show that T is what?
Diagonal?
Diagonalizable. So there exists a
Diagonalizable, right.
basis with respect to which it's diagonal.
Yeah.
We're going to prove that and more.
Yes.
Yeah. I mean, I think we're ready.
Yeah, that's it. We don't need anything else.
I think we're ready for.
Oh, is that
the-
spectral theorem?
Yes, the spectral theorem.
Ah, I see.
Yes. Well, it's one of the many, many spectral theorems that
It's one of-
exists,
Ah.
and this is like the simplest one.
So
It's one of those theorems where there's a bunch of different.
How many order?
There's a bunch we didn't.
How many order?
I don't know. Cause you have the spectral theorem for self-adjoint operators, you have the spectral theorem for normal operators, it's all the same theorem. But then when you start looking at infinite dimensional vector spaces, then there's spectral theorems for bounded operators, and they're not quite they say something that's not exactly this. They say something else. So there's quite a few which are like, it's essentially the same theorem, but just generalized on a more and more,
Complex vector space.
no, not complicated, if anything, less restricted vector space, right? Having finite dimensions is very restricted. So, yeah, like the usual one is like you have a bounded operator on some inner product space, and then you get that its spectrum is pre-compact or something like this. I don't remember.
Okay, so. Okay, I'll just read it. See what it's doing.
Yeah. If we're working in a complex vector space and T is self-adjoint, then there exists an orthonormal basis of eigenvectors of T, which is a very nice basis.
Yes.
It's just about everything you could ask for.
Because then T just becomes what? It just becomes, let's multiply by a number on
Yeah.
this subspace.
So you can have like a square that goes
Yeah.
like this.
Well,
Yeah.
how big
Basically.
is-
Sorry?
Well, how big is-
Yeah.
Sorry.
Well, it could get smaller.
Oh,
Okay.
yeah.
Yeah. Maybe. So yeah, the proof is very simple. First, okay, recall from some of our previous lectures that every polynomial in C splits, right? And we proved in, I believe, our first lecture that if the minimal polynomial of T splits, then T has an upper triangular basis with respect, or an upper triangular matrix with respect to some basis. And then when we were talking about the inner product, we talked about the Graham-Schmidt procedure. And one of the consequences of the Graham-Schmidt procedure is that if you have an upper triangular basis, then you can construct an orthonormal upper triangular basis. And so all of this together means that there exists a basis of vectors such that T with respect to that basis is upper triangular. Oh, sorry. And it's orthonormal. Whoa. Whoa. Okay. This is an orthonormal basis, and T with respect to it is upper triangular. Okay.
So this is just, we know from before.
So yeah, this is like, it's called Schur's theorem, Axler calls it. So next, recall from 10 minutes ago, we proved that, the matrix of T dagger, with respect to, again, these are orthonormal bases, so our theorem from before applies, which is equal to the basis of B, is equal to, I'll introduce this notation. It's the conjugate transpose.
What is it? The second step, was it the conjugate?
This is the adjoint. This is the adjoint. It is. Maybe I should write it maybe in a different way. Let's start.
So you should say that T dagger in beta is equal to T.
Beta, which is equal to like we.
Sorry, you're using two properties at once. Let's go one step at a time.
Okay.
No, I
Okay.
see that you brought, but yeah, sure.
Yeah.
Like
Oh,
do this, and then that is equal to
And then
like transpose and complex conjugate
which is equal to, well,
of T.
yeah.
So write that first, and then say recalling that T is self-adjoint.
I haven't introduced the notation, so I'll just.
Sure. Yeah. Okay.
So, and you know, if this matrix is upper triangle, then the conjugate transpose of it is going to be. You're going to flip. Yeah,
Yes.
it's going to be lower triangle. Now, we have, and this is upper triangle. Now you see, we have that T is self-adjoint. And then that means that these two matrices are equal. And oh boy, what does that mean? It means that this matrix is both upper triangular and lower triangular. And so,
Must be.
yeah.
Oh. Oh, 0. Hey.
Yes.
Hey. Oh, that's nice.
And the other thing is, you know that the stuff on the diagonal has to be equal to its complex conjugate, right? Because it's conjugate transpose. So you kind of get that for free.
Yeah.
Okay. But, you know, this proof is, you know, it doesn't refer to any basis,
Okay.
so, okay, alright.
And
Yes.
then the result follows.
And so now we have this amazing, wonderful idea, okay, of the spectral theorem. That if I have any self-adjoint operator, it has an orthonormal basis of eigenvectors on a finite dimensional vector space. Okay. And so this is a result that we will kind of assume is also true on an infinite dimensional, in the infinite dimensional case. Actually, if your basis is countable,
If it's separable.
Countably infinite?
yes, countably infinite, then actually this argument should still work. It should be completely the same. Why? Because, so let's kind of go back through, oh right, the only thing that would be non-trivial to prove is this thing with so the thing that would be non-trivial to prove is showing that there exists a basis with which the matrix is upper triangular, because with Axler, the way we did it most recently was with
The minimal polynomial.
the minimal polynomial. However, you can kind of take that proof by reading the older older edition of Axler.
Okay.
When the older edition of Axler, he doesn't refer to the minimal polynomial. He just does some induction on the dimension of V. And I mean, in our proof, we also did an induction on the dimension of V. We just referred to the minimal polynomial. But the point is, if I have like some countable infinite dimensional vector space, then I can just do that proof. I can just do that same proof with an induction on the dimension of V just infinitely many times, and I get the result is true for like a countable number of dimensions. Then the proof with the orthonormal basis, that if I have a basis, I can turn it into an orthonormal one with some property. That was also some inductive algorithm that was inductive, and so then I can just apply this algorithm to some countable list and get a basis out of a countable list. That's okay. Then this thing about the matrix, okay, well, I can still have like a for a countable, I can still have like an infinitely large matrix, and the entries in that matrix would still fully determine how I send my vectors on the basis. So that would still fully determine how my operator acts. So I can still have a notion of matrices for an infinite dimensional vector space if it's countable. And this whole conjugate transpose thing will still work, because if I have an orthonormal basis, then I still have this property of like TEJ inner product Fi gives me the right whatever. So essentially, this theorem works for sufficiently nice infinite dimensional vector spaces, and we will just kind of assume that the vector spaces we work with are sufficiently nice, because proving that they are indeed sufficiently nice will sometimes, it will take just, like a while, and it's besides the point. But okay.
Wouldn't you need some like Artinian-like property that T of V due to K of V eventually is stable?
Is stable? What do you mean? That it's like bounded. Yes, T would need to be bounded. That's right. Yeah, we need T to be bounded, and this is the thing that okay. Okay, I'll just start making comments. Do you have anything else to?
No,
or is
no,
this,
no,
yeah.
no.
Okay. I'll just start making comments.
Should I give you?
I mean, sure. I usually talk loudly enough that it doesn't matter. I don't want to write anything. I'll just make comments.
Yeah.
So, first thing. Remember that we defined how we define T star, right? T dagger. T dagger we defined using the Riesz representation theorem as something that. So we said that. So let T be from V to W, okay? And then we said that, so if there was something, if there was a T dagger that goes the other direction from W to V, such that T of V W was equal to V T dagger W, if we had something like this, then we call it the adjoint. And we showed in finite dimensions that the adjoint always exists. But for that, we used the Riesz representation theorem. And the Riesz representation theorem really depended on the fact that we have a finite dimensional vector space. In infinite dimensions, it is not always the case that T dagger exists. Okay? And oftentimes, it doesn't exist on. It doesn't exist. So oftentimes, what you're not interested in a map from V to W. You are interested more in a. I'll erase this because this we've discussed a while ago. Oftentimes, you are. Oftentimes, you're interested in T being from V to V, so T a linear operator. And oftentimes you do not have T dagger does not exist. T dagger does not exist on all of V, but sometimes you can kind of take T and restrict it to some subspace D, and on this subspace D, there exists a T dagger going from D to D, such that it has this property.
Then would D be finite?
Not necessarily finite, but only for vectors VW in D. Okay, so this is and then you have to start worrying about what exactly this subspace is and trying to find it. But yeah, this is something to worry about. That in infinite dimensional case, T dagger is not necessarily defined, and you have to be careful. And you have to be, and there it starts mattering if this operator is bounded or not. And okay, we haven't even talked about what it means for an operator to be bounded. But yes.
Does it have to do like with the norm of the linear map? Is that
Yeah, that's exactly right.
Okay.
If the norm of the linear map is defined, it's bounded. If it's not defined, it's not bounded. Okay. So Good. But now, why did we? So you actually raised a really good point, and I didn't think of explaining it like this, even though I knew that this is a way to explain like this. So remember, what do we want to do in the end? We want to do quantum mechanics, right? In the end. And so, just now, what Alisher said is that we got some generalization. Well, not generalization. We got something that is kind of like we have an inner product space, and we have linear operators on the inner product space, and then we have this kind of dagger operation. Do you agree? That takes me from LV into LV. Do you agree? If I take a dagger of an operator, it takes an operator and then gives me back another linear operator. Very good. And we realized that this is kind of like complex conjugation, right? Roughly. And then we realized that if T is self-adjoint, it is kind of like a real number. In the sense that there exists a basis of eigenvectors and all the eigenvalues are real for T self-adjoint. Okay, that's very good. So what role are self-adjoint operators going to play in quantum mechanics?
The unitary matrix, like some gates.
Not quite. So if I'm doing an experiment in the lab, what does it matter? Like where? I mean, actually, this is a very hard question to answer. You won't guess.
Able to reverse, like once you apply this operator.
That's not quite. Unitary matrices aren't necessarily. Yeah, sorry. No, that's not quite.
Okay,
Yes.
no worries.
I was told like one of the nice things about self-adjoint operators is that their eigenvalues are real, so you can
Yes.
measure them in a lab.
Exactly. So that's the point. If why would I want something to be real in physics? Is because things that I measure in the lab, I always measure a real number at the end of the day. Do you agree? So, in some sense, and this is what you kind of have in classical mechanics, right? In classical mechanics, observables, they are some functions of a position and momentum, that output a real number. Do you agree? And here we have, we found self-adjoint operators that are somehow like real numbers. And so I see that self-adjoint operators will be related to what? To observables. In fact, we'll call self-adjoint operators observables in a little bit. But, and it's not going to be quite like this. This is not going to be necessarily a function of like some position and momentum. It's not going to be like this at all.
Yes.
But the analogy is kind of like, if I measure something I want it to be a real number, my quantum mechanics is going to be something about, Hilbert spaces, vector spaces, inner products, and it's going to have complex numbers. So if I want to measure something, I want something to be real. So whenever I start talking about measurements, I will need to have self-adjoint operators appear there somewhere in some sense. Okay, I'm being vague because if I told you now, then we'll have less things to talk about next time, and it's already overtime. But this is kind of why we care about this, is that at the end of the day, I want to be measuring real things, and this will, help. The important thing is, what's the, this is what physicists will say, what's the big difference between self-adjoint operators and actual real numbers? And I mean, in general, what is the difference between operators on V and complex numbers? Well, one of the differences.
You can measure one.
No. There's nothing.
Okay.
In math, there's no sense in what to measure. That doesn't make sense.
Like this, like.
I mean, you have notion of distance for complex numbers too. You can take absolute value of complex number, yes.
There's not a field, for example?
Yeah, but okay, sure. But which part of them not being a field fails?
Invertibility?
Okay, invertibility, give me another one.
Commutativity.
Commutativity. That's the big one that's really important in quantum mechanics, is that if I have invertibility matters less, but the fact that things don't commute, right? If I do t and s, that's not necessarily equal to s and t, and that is kind of the big difference. Where in classical mechanics, your observables are always real numbers, and so those commute, and so that's fine. But then in quantum mechanics, you see that your observables will be the things that you can observe. You will somehow extract out of some self-adjoint operators, but these self-adjoint operators will not necessarily commute, and so that will be a problem. Well, not a problem. It will be a feature which is kind of very, very unintuitive at first, but it says many things. And for this reason, it will be very special when things do in fact commute, and that will help us simplify problems by a lot when things commute. And in fact, I think one of our sessions will be precisely on talking about the case where things do commute and why exactly that is helpful. And it's, in terms of the linear algebra of it, it's a very simple idea, but in terms of the physics of it, it kind of has things to discuss. But yeah, that's it for today. Thank you all for coming. Yes, clapping for you. Good presentation.